is just record. Okay. So yesterday, right, we talked about how if you have a charge, it produces an electric field. We actually did some calculations on how to calculate the electric field from a single charge, meaning a point charge, right? This is just Q over R squared R hat, right? So let's say you have a little positive charge here, and you always just assume that the charge is positive when you're doing these calculations. If it happens to be negative, you just do the calculation as if it's positive and just reverse the sign at the end. Okay. So you have some charge here, and let's even put like a coordinate system. Like let's just put the charge at the center of the coordinate system. Okay. And I'm interested at the electric field at this point P, right? This point is not, it's just some label P. And this electric field is going to be some vector. If in case of a positive charge, right, we expect the electric field to go away from the charge. If it's a negative charge, then it'll go towards the charge, right? So, and then if you have multiple charges, right, let's say you have, I think yesterday we did this example, right, where we have 3 charges, right? You have electric field from each of these, and then, right, the net electric field is actually all 3 of them added together, right? So you have multiple charges, you have to add these electric fields together, okay? What we're going to do today is that, well, what if instead of 3 distinct charges, what if we have a continuum of charges? Basically, all the charges are actually kind of spread, let's say, on a rod, right? And in case of a rod, we need to know this quantity called the charge density per length, right? Which is symbolized with this variable called lambda, right? Okay, that's for in case of a charge distribution that's on a stick, right? But if it happens to be on a sheet, you can also have a 2-dimensional version of this, right? It's the same name, right? It's a charge density, but instead of per length, we have to deal with per area. So they changed the symbol for it to be eta, okay? But the last one we talked about is that what if you have like a 3-dimensional object, right? I don't know how to really draw a 3-dimensional object, right? And then you have a bunch of plus charges on here, right? If you take a little piece of it, right? This also has some charge density. And for the 3-dimensional version, right, that's actually the symbol rho. It's kind of like writing a P, but like, like backward like that. Okay, and this will have units of coulombs per cubic meters instead, right? So that's the SI units. The SI units for charge is coulomb. The SI units for volume is meters to the 3rd power. Okay, but before we can jump into trying to figure out how we can calculate the electric field from these weird objects, right? What we're going to do is we're going to go from a realm of adding up the different charges, the electric field from different charges, to what you learn in calculus, where you're going to turn that summation into a integral, right? Summations are basically just integral as you take delta t as it goes to 0. What we're going to do, instead of delta t going to 0, we're going to take like delta x as it goes to 0. And we're going to figure out how we can change that into a integral. And that way we can actually do the calculus we need in order to make the computation, as opposed to just trying to add up like, 10,000 charges, right? Because that would be hard to do. Okay. So in this little example here, we have some rod that has some charge density lambda, right? And you can see that the total charge of the entire stick is Q. The length of the stick is L. So the charge density, we actually can write that right away. It's just the amount of charge on the stick divided by the length of that stick, right? In here, right, initially what we want to do is that, well, there's some charge delta QI here, right? It doesn't have to be that point. I can pick any point on the stick, but it's just picking somewhere in the middle here, okay? This has some amount of charge here, right? So therefore, if we add up all the charge, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say you do that summation, right? When you do that, right, you add up all the little bits of charge, right? You get the total charge on the stick, right? If you add up the charges on all the stick, right? That's still Q. We're not doing anything fancy here yet, right? So, but what you can do, instead of doing this summation, okay, we can take the limit as these little tiny charges as opposed to, oops, I didn't mean to type that S, right? As opposed to trying to just saying, oh, there's 10 little lumps of charge. What if I make that like an infinite number of lumps, okay? Meaning each of the little piece of charge is going to 0, right? So if I take if I take something, let's say it has like, 10 coulombs of charge, right? And I cut it into 10 pieces, each of the pieces will have 1 coulomb. But if I cut it into 1,000,000 pieces, each of them will have 10 to the minus 5 coulomb or something like that. But if I take it into like, cut it into like millions times millions times millions times millions, right? Meaning infinite number of pieces, each of the charge is actually going to 0, right? As the limit of number of cuts you make into this stick, the amount of charge per slice is going to go to 0, okay? So therefore, if you take the limit as the number of charge goes to 0, you turn this summation into an integral, right? And that's the idea of calculus, where you can actually turn summations into integration. And then we know how to do different methods of integration, and we're going to see a couple of those today, okay? So if we're interested in calculating the little tiny bit of charge on there, right? A tiny bit of charge, let me just redraw the stick here, right? Right, a tiny bit of charge, right? We're interested in a little tiny bit of charge here, dq, right? That amount of dq is actually equal to the density, the line charge density, times dx, meaning dx is the little sliver of distance that we actually multiply that the charge density by, okay? So this is valid for any line charges, okay? So instead of trying to integrate dq, what you end up with is you can replace dq with lambda dx, right? When you do lambda dx, right? Therefore, now you can actually do that integration as a function. Let's say, this coordinate system here, this is x, right? So you can actually integrate from, let's say, x equal to 0 to x equals to L, okay? And so that's how you deal with that, okay? So that's the transformation from, doing this summation of like 3 charges, 30 charges, 3 million charges. But now we're going to do a summation with infinite number of charges, right? That are all distributed along this little stick, right? Infinite numbers of tiny charges, right? So infinite times a small number is actually a finite number. So that's the wonky thing about in calculus, right? Okay. So what we're going to do is that we're going to use this line charge density and this method of changing your summation into an integral in order to calculate what is the electric field. Let's say you have a stick that has a length L, right? What is the electric field some distance lowercase r away from that stick, from the center of that stick, okay? So what you want to do first is that since I have this picture, usually you have to draw the picture yourself. Since I have this picture, I'm just going to randomly pick a little piece of charge here, right? I'm going to call that delta Qi, okay? And that delta Qi is going to create an electric field at my point P, right? I mean, R away from it. So it's going to be like, kind of like this direction, right? I'm going to call that EI. Okay, so I can calculate what this EI is, okay? So this is jumping away from it's kind of more like the setup part of it, right? This EI, right? I can calculate this because since this charge is so small, right? I can use the point charge equation for it, okay? So the point charge equation for it is 1/4 pi epsilon naught. Well, the little bit of charge here is delta Qi, okay, like that, divided by the distance away from it, which is not R, right? Right. So let's label that like, I don't know, R. I don't want to use the prime. Let's just use the letter D, okay? Square, right? And it's going to be some R hat square. Well, since I'm labeling that D, we should actually use D square. Actually, is it okay if I just change this letter to D? It's just annoying that the book is not So I'm going to change that the letter to D, and therefore now I can use this R as the distance, right? Which is exactly the same formula we had before. Okay. Okay. So instead of the distance away from the rod being R, I'm just going to call that D instead. Okay. We may have to suffer some consequences after that. Okay, but that's for a point charge, right? But that's only for one charge, right? In order for me to calculate the electric field for all the charges, right? I'm going to have to add up all the different electric fields, right? So the net electric field, E, the total electric field, is the sum of all the little tiny pieces of electric field I just wrote down, right? One thing about this problem, just as we found out from the 3 charge situation, right? If you have a charge up here and you have a charge down here, right? Which component of the electric field is going to cancel each other out? The Y component, right? So, because if I have, let's say, I put a little green charge here, right? This is going to produce an electric field this way. So the Y components are actually going to be 0. But the X component, they actually are in the same direction. So they actually double each other, right? Okay. So we know that right away. Let's go back to red. EY, which is from this piece, right, is actually 0. But we have no idea how to calculate what EX is yet, right? Yeah. Okay. So we're going to apply the concept of finding the total E field as a vector using, the summation is going to be to integral technique that we just learned, right? And knowing EY is actually 0 due to, so this type of stuff they can do is known as symmetry, right? Because the problem is symmetric in the Y direction, you can use the symmetry to say that EY is equal to 0. So we just have to calculate what EX is. Okay. Okay. And that's going to be the like a probably close to a page of calculus in order to do that. So let's do that. This is the solve part, right? How the heck do we find EX, right? So EX is going to be the sum of all the little pieces of EX that we're going to have, right? Ooh, okay. Okay. Okay, so looking at this situation here, right? So let's replace what EIX is, right? You have this big summation stuff still, right? So each of the individual EXs, right, is going to be just the X component of this, which is EI times, if I declare this angle, let's call this angle theta, right? Right. Even though it's not the problem, I'm going to call that theta, right? And that's going to be cosine of theta. That will get me to EX, right? EI, ooh, sorry. EI just comes from this formula here, right? That's the magnitude of the electric field. Okay. So you have big summation again. 1 over 4 pi epsilon naught, the amount of Q divided by R squared, okay, multiplied by cosine theta. Instead of writing cosine theta, right, remember cosine theta is this angle here. Cosine is the adjacent over the hypotenuse, but that's the same angle as here. The adjacent over the hypotenuse is actually D over the distance R, right? So cosine of theta is actually the same thing as D over R. Okay. Right. D over R from there. All right, let's get to the next step. Okay. And R, right, is this complicated thing from Pythagorean theorem. It's just the distance square, the D square plus, right, whatever this Y value is square, right? Okay. Okay, so, oops. Summation, a lot of copying involved, delta Qi, right? And I said that this is R to the 3rd power, right? So this D square plus Y square to the 3/2 power multiplied by D on top. Okay. Now, right, we're going to use our summation to integral method, where instead of a summation over all the charges, right, it's the same thing if I take that delta Q as it goes to 0, that's the same thing as an integral, right? So I'm going to pull this integral. So instead of writing delta Q, I'm going to write dq, right? There's that d still around. So the d, there's multiple meanings of d's around, unfortunately, right? Maybe I shouldn't have picked d as the variable. Okay. So now we have this crazy looking integral here. And it's even crazier because, right, we're trying to integrate charge, and d, the other d is the distance, that's a constant, but y is a variable, right? Y changes depending on where you are on the stick, right? So y is equal to 0 here, y is 1, 2, 3, it changes, right? That's the variable, right? So now we have an integral that we're trying to do, but the variables don't agree with each other. So we're going to have to change dq somehow, right, into something that's going to be dy instead. Something dy, right? Because that's the only way we can do that integration. Okay. So looking at this stick up here, right? Right. If we want just a little bit of charge, right? That's actually the charge density times the little bit of distance in y that we moved, right? Okay. So so if we take a little sliver of dq here, right? This is actually the line charge density multiplied by dy, right? Right. So now we can replace that, right? The line charge density, right? The line charge density is actually the total charge divided by the length of the thing, right? So we can actually, dq is actually q over L times dy. And now we can replace that in here. And I'm gonna do algebra in the going left direction because I'll just run out of room otherwise. I'm gonna pull all these constants out because that's a constant, that's a constant, right? So d over 4 pi epsilon naught integral of d, instead of writing dq, I'm gonna write q over L times dy, right? And then the rest stays the same. Hopefully I'm doing this right. Okay, these are also constants, so we can actually even pull those out. Okay, so d times q over 4 pi epsilon naught divided by L. And now you have this gnarly integral of d squared plus y squared to the 3/2 power. Okay, so those of you in Calc 2 or have taken Calc 2, this is actually done using a method called U substitution. Does that sound familiar? In this class, you don't have to do that. If we're doing this type of integral, I'm going to give you an integration table, okay? But you have to know how to use this integration table, okay? So in Appendix A in your book, you can look this up. So some of the integrals down in here is for example, if you have integral that's in the form of, right, dx over x squared plus or minus a squared, where a is a constant, to the 3/2 power. The reason I'm picking this is because I see down here there's a 3/2 power going on, right? So we have to deal with this 3/2 power thing, okay? Right? And then there's another one that actually has an x dx in front, so it actually has the variable that we want, that we're integrating against. I think in this case, we don't have that, right? We don't have a y on top, right? Unless I forget a y. Double check that I didn't forget a y. Where did I forget the y? The q cosine. Just want to make sure that, because I think the book does have a y in front. I blurry because of the printout. Cosine of theta X over Ri. Okay, so I don't know why the book is doing it that way, but hopefully we'll end up with the same answer. Okay, which is this stuff here, R of a rod. Okay, so we'll see how that turns out. Okay, all right, so we're gonna use this form of integral because we're, instead of x's, you basically think of them as y's, right? Because we have y's instead, okay? So what this integral will turn out to be is basically you lower the power from 3/2 to 1/2, right? And then instead of, and when you do this integral, the x just turns into the dx turns into an x. And then you also have this factor of a squared in front, okay? So in our case, that's going to be the distance d, okay? So if we were to complete this integral, right, d times q, I'm going to put a little star here because it's not dq, okay, 4 pi epsilon naught L, right? This integral turns into just y, okay? So instead of x, we have y, and then instead of a's, we have d's, right? So that's actually d squared in front, okay? And then square root of y squared plus d squared, okay? And that's what the integral turns into, okay? And this is going to be evaluated from, well, where's y, where's the limit for y, right? Because this is the y equal to 0, okay? So this is actually y equals to negative L over 2 to positive L over 2. Okay, so we have to evaluate this integral from negative L over 2 to positive L over 2. Okay, and let's see what happens when we do that. Okay, the next line, right, dq 4 pi epsilon naught L. Okay, we plug in L over 2 on top, L over 2 on the bottom, squared, d squared, minus, right, L over 2 with the minus sign on top, and then basically the same thing here. But you can right away, so you can tell that these two minus signs are going to cancel each other. So basically, you know, the second term just basically doubles the first term. Okay, so I'm not going to write up all that stuff. Okay, so I'm going to keep going. D times Q, oops, D times Q, 4 pi epsilon naught. Okay, so since it doubles, this factor just goes away on the bottom. Okay, L squared to over 4, hopefully you can see that, times D to the square. Okay, these L's actually cancel each other out. One factor of D cancel each other out. Okay, so the answer you end up having is 1 over 4 pi epsilon naught, the total charge on the thing, D times L squared over 4. Ooh, right, this is to the 1/2 power, right? Forgot about that, because I left that out. Okay, plus D squared to the 1/2 power, okay? So that's what it's that's what it looks like, okay? Okay, so that's in the case of a rod, right, that has some length L, and you want to figure out what the electric field in the x direction is for that case. So if you want to write the final answer, because that's going to be a vector, right, the electric field vector itself, right, is this number, Q over D, L to the 4th plus the 1/2 power, and it's all going to be in the positive x direction. Okay. Ooh, okay. We're going to do some limiting case on this, where we're going to try to figure out, well, in the case where L is much bigger than R, right, it's actually the same answer here. So the book uses, instead of the distance D, it uses the distance R away from it. So that's why in the next part of the notes, just pretend all these R's is the distance out, which is the variable I use, okay? Okay. So in the case that L is much bigger than R, meaning, let's go back up to the picture up here, right? The length of this rod is very long compared to the distance you are trying to calculate the electric field. So you're either very close to the rod or the rod is just very long, okay? So in either of those cases, right, well, you can say that, well, if L is much bigger than R, right, this term is much smaller than the second term, right? 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 If this number is big, this number is small, this term is the one that dominates. That's the one that matters, right? If this is 10, this is 1, right? 10 squared is 100, 1 squared is still 1, so 101 is basically approximately 100, right? So when you simplify this, what happened is that the electric field from a rod simplifies, to just 1 over 4 pi epsilon naught. The reason I'm not canceling out the 2 is because 1 over 4 pi epsilon naught is a nice number. That's just K, right? Twice the charge density divided by the distance away from it, and that's it. Okay? This is if L is much bigger than R. Okay. Okay. And this is the approximation we're going to use a lot since we just derived it. Okay. Where if you have a rod that has some charge on it, right? If you're close, the electric field is pretty strong. As you go further and further away, it drops off as 1 over R, as opposed where if you have a point charge, right, it drops off as 1 over R squared. But if you have a rod, this drops off as 1 over R instead. Okay, so that's the main difference between the two. Okay. So in the homework, instead of dealing with it on the rod being vertical, you're going to have to deal with the rod being horizontal. And that's just another integration technique that you're going to get to play with. Okay. So we're going to see that in your homework. But before we jump into the worksheet, I want to show you guys this one next example where it's going to help you get started on your worksheet. Okay. So I'm going to show you guys how to calculate the electric field due to a ring of charge instead. So you can actually see on your worksheet, right? It's actually a semicircle instead of a full circle, and that's going to give you a different electric field. Okay. So interestingly, this is actually a simpler version, a simpler problem compared to the line charge. Okay. So in this situation, right, you have some ring, and we're going to put the ring, the center of the ring, at the coordinate, at the origin. Okay. And we're trying to figure out what is the electric field at some point P, which is, along the Z-axis here. Okay. So it's actually equal distance no matter where you are on the ring from it. Okay. Okay. And we're going to try to figure out what the electric field there is. Okay. So once again, we're going to apply the same techniques as before, where we pick a little piece of charge up here, right? And we're going to try to figure out what is the electric field from that little tiny piece of charge, right? It's always going to be 1 over 4 pi epsilon naught. The little piece of charge, okay, divided by the distance square, right? And it's going to be in the R hat direction. Okay. Right. And I think the book uses RI, so I'm going to do the same thing. Okay, QI, RI. Right, these are all little I's. Okay. So that's the electric field we're gonna, that's from this charge, right? That's gonna produce an electric field here. From down here, right, if you have another charge, right, you do have another charge here, it's gonna produce the same electric field going this way. So actually, any electric field, right, going in the Y direction, once again, this is EY, I, and this is, I opposite, right? They're going to cancel each other out once again, right? From the symmetry of the problem. So the only electric field we have is going to point in this direction, right? So we just have to calculate that one, okay? So only EZ is not equal to 0, right? So we just have to calculate that, okay? So how do we figure that out? Okay, so EZ, the ith little one, right? The little tiny, from the tiny bit of charge, is going to be 1 over 4 pi epsilon naught. The little bit of amount of charge there divided by RI squared. Right, and once again, I'm gonna declare this angle theta I, right? If you multiply by cosine of theta I, that's gonna be that part, right? That's gonna project it out to the Z Z component, right? All right. So once again, then what we do is we have to sum up to get the total electric field in the Z direction. We have to add up all the little tiny pieces of it. Oops. Z comma I, right? You have to add them all up. Okay. When you add them all up, you turn this summation into an integral, right? Right. And so instead of writing, delta Q, when you turn it into integral, you turn that into dq, right? Right. Epsilon naught. And this is still cosine of theta. And remember, cosine of theta, right, is adjacent over the hypotenuse. So adjacent is actually the distance z. The hypotenuse is actually Ri, right? Or Ri, oops, not square. And then this last part here is still Ri square, okay? So this is the cosine piece, right? Okay, sorry, my epsilon knot sucks, okay? There it goes, okay? So once again, we have some value here that we want to try to calculate. So this case is kind of special though, okay? Notice that the value z, right, it's the distance out. As you go around this ring, the z doesn't change, right? So that's a constant, right? Right? The radius distance out here, right? As you go around the ring, it's the same distance to p, right? So that doesn't change, right? So that's a constant, that's a constant, that's a constant, that's a constant, that's a constant. So all of that can be pulled outside the integral, okay? And this is a very important point, where z, I'm just gonna write it out 1/4 pi epsilon naught, right? Z over Ri to the third power. All of those are constants, right? And so the only thing you're integrating is actually the integral of dq. And who knows the answer to what is the integral of dq over the ring if the total charge is q? It's just q, right? If you add up all the charges, right, all the charges has to add up the total charge, okay? So 1/4 pi epsilon naught z Ri to the third power, R to the third power, R to the third power, Ri to the third power. And this is going to be the total charge Q, okay? Ri, once again, right, we're going to use Pythagorean theorem to figure out what this distance is, right? Is z squared, let me just write it down, right? Ri is going to be equal to square root of z squared plus the radius of the ring square, right? Because that's just the triangle we're dealing with. So we're going to have to plug that back down to here. So Ez, it's 1/4 pi epsilon naught, z times q, right? Just put that in front. And then z squared plus r squared. Come on, right? Don't think. I think the app just crashed, okay? Did it not save anything? Let's see, save it. Let's see how much math I have to redo. And now, oh, that's not too bad. R squared to the 3/2 power, okay? So that's the z components of the electric field. So if you want to write the entire thing, right? The vector is 1/4 pi epsilon naught q times z over z squared plus r squared 3/2 power times k hat direction, right? Because that's the direction, right? So these two problems with the line charge and the ring charge is going to help you deal with the worksheet we're going to deal with today, okay? So let's get into our color groups.